we're good. Excellent. Well, thank you all for joining me today, bright and early, at 9 o'clock, first session. So we'll get going. Hopefully you have your coffee. So I'm Matt Colgrove, as John mentioned. I wanted to mention one other thing. I've been with PGI for about 14 years now, or 13 years. And a large part of the last, 5-6 years have been on OpenACC. A lot of my job is to be the point to the customer in terms of understanding, what you're trying to do with the language and how we can develop either the standard or the PGI implementation for that. So a lot of today's talk is on C++ with OpenACC, and this is coming out of work that I've been doing with Sandia, as well as a hackathon that was going on last October at Oak Ridge National Laboratories with some C++ code. So first of all, how many people actually know OpenACC or have exposed to OpenACC? Just a few of you. Or actually, okay, good, more than half. So this talk, I'm not going to go into really in depth about OpenACC, but I thought I'd just give a brief overview for those of you that may not be familiar with it or just wandered in wondering what this thing was. The idea behind OpenACC is you divide up, well, I should say first, OpenACC is targeting a generic concept called an accelerator. An accelerator can be an NVIDIA GPU, and that's what I'm going to be talking about a lot today since we are at an NVIDIA conference. But it could be an AMD Radeon, it could be an AMD Kavari APU system, it could be an Intel Phi, it could be an FPGA, it could be anything that is a heterogeneous architecture. And by heterogeneous, well, also we're looking at highly parallel heterogeneous architectures. So there's a discrete data, or discrete memory between the two. So we actually have to manage our data between them back and forth. So the idea, if you're familiar with OpenMP, behind OpenACC was what OpenMP did to pthreads, OpenACC is to do to CUDA. In other words, we're going to try and make it easier, more accessible. Parallel programming is never easy. Don't think of this as going to be easy. In the C++, it's actually more of a challenge. It's not easy. It's just making it easier access for you so you don't have to go down to the lower level CUDA. So you define a region of code, in this case, Pragma ACC. ACC is the Sentinel kernels. It says, compiler, take all this code in between these two brackets and offload it to the GPU for me. And at a bare minimum, this is what you need. And there are more complex things that you can add, and more. There's a whole nother parallel compute Sentinel as well. Slightly different direction, but at the bare minimum, this is what you need. You need to be able to say, okay, offload this to the GPU. And then if you notice there's a host code here, an iteration counter. Well, the compiler at this point needs to get the data over to the GPU, and will do so. But if you're doing this in an iteration on the host, what are you doing? You're copying it back and forth each and every time. So we invented the concept of a data region. And this is a structured data region where it says, OK, copy the data to the device at this point. When you execute it on the device, you reuse that data over and over. You don't have to do the copy back and forth. And when you get to the end of this structure, you bring it back. OK, so that's your 2-minute intro to OpenACC. So now we're going to get into some more advanced concepts, and OpenACC, particularly with C++. Now, about a year ago at GTC, if your C++ program looked like C, you could use OpenACC. Otherwise, you couldn't. Really, the support was lacking. So we've spent a lot of time over the last year thinking, well, what are the concepts that we need to provide support for, at least to get you access? First off, the this pointer. That turned out to be the biggest key to C++. That enables now you to access data members. Before, you would have to do a pointer to your data members and then use those in an OpenACC region, because there's an implicit this pointer on all your data. Allows access to all your methods. There's also some other concepts, routine in OpenACC, which I'll get to in a minute. So also we recently added full compatibility with G++ on Linux. So we're fully object compatible with G++ there. That has nothing to do with OpenACC, but the marketing department wanted me to put that in there. But one thing is we're not done yet. There's still a lot left that we have to do to get full support for C++. So I'll describe today where we're at, and then at the end we'll talk about where we're going in the future work. And a lot of this is being driven by our collaboration with Sandia National Laboratories. I've got weekly or bi-weekly meetings with them and really looking at how we can support the national labs and their C++ efforts. Okay, so let's look at a class with OpenACC in it. Or excuse me, this is the main program that's using a class. And here I'm just going to be a generic container type. This is my own container type. I'll talk about vectors later. But my V type has a float. It looks pretty simple. So here I'm using ACC parallel. This is the other compute directive that you can use. So it says, go ahead and parallelize this loop. Assume no dependencies in here. Well, there's actually a lot going on just in this little loop. Well, first we've got to create the class up here. We're going to initialize the two classes. Well, these brackets, well, they're really function calls. So, I mean, yes, they get inlined. They're really operators. Operators are really function calls. There's the size operator being used. This is actually just got supported in our 15.1 compiler. We didn't have support for this before. These plus equals operators, well, they could be methods too. We don't know what that plus equal really does. It could be a function call. It could be doing all sorts of interesting things here under the hood. With C++, you kind of extract that away. The other thing I did need to add is the explicit data movement. So data movement is very important for performance on accelerators because it costs a lot of time to copy data back and forth. So one thing I could do is I could encapsulate my data movement inside this class and hide it from the end user. That's one possible. But you want to be able to do it in aggregate in big chunks. So in this case, I've exposed that data movement to the user, but using methods. So I've had to add methods to my class in order to allow the users to explicitly copy the data at certain points. Now, the exact details of how that data is being copied is still left up to the class. But now I've just put the emphasis on the user when using my class of when to actually do the data movement. So pretty simple. Within the class itself, with OpenACC 2.0, that's the latest version of the spec, we realized that structured data regions that I showed on that first slide where you say start here, end here, didn't work well for classes. So we came out with the concept of a unstructured data lifetime. So the idea here is now you can match where your data is being allocated or dynamically created with its movement over on the device. And that naturally falls into a C++ constructor in destructor. So when you instantiate your class, you can, at the same time, within your constructor, create a device copy of your data. So that's what's going on here. Well, first, we actually have to create an instance of this class on the device. So we're going to copy in the this pointer. And once we do this, what we're doing is we're actually creating a shallow copy of our host data members. So the size is being copied in at this point, and the data pointer is being copied in. And I said shallow copy. That's important because it's the value of whatever data is. That's a host pointer at this point. So when I do this data copy in this, I'm copying in actually the host pointer. It's not what we want. So what we do next is then create the data onto the device. And this does two things. It actually allocates space on the device, but then does an implicit attach. And by attach, I'm meaning that the compiler is going to fill in the device pointer back into the data. So on the device, you actually attach, or actually, so now when you call this data on the device, or use data on the device, you are using the proper pointer, using the pointer on the device. If you reverse this and did data first, that attach would not happen, and you'd be using the host pointer. So order does matter in this case. And then down here in the destructor, you actually use the exit data. So you do enter data. That's your data, unstructured data regions or unstructured data lifetimes. And then you would actually delete it here down in the destructor. Now, within your class itself, you're going to have methods. OpenACC 2.0 also introduced the concept of a routine. And a routine allows you to create a device function, so a device callable function. And it implicitly creates it for you here. So we're going to say, oh, compiler, I need to, whenever I call int values on the device, which is down here. So we got this initialization. Oh, we're going to initialize on the loop. So if I'll go back one slide or two slides here. So we've implicitly created x and y on the device. And we call this init. When init gets actually executed, it goes in and initializes the data on the device. You could also, initialize it on the host and then copy it over the device if you want to synchronize. Up to you. This is just for this example. I just did the initialization only on the device. You can call init values of other methods, and then this just calls this function. So it's true function calling. Then right here, I've added my copy methods. So when the user calls update device from the main program, it does this update device. Update is when you have a data region, at some points you need to synchronize or make the data between the host and the device. This is how you do it in OpenACC. You say update host or update self. Yes? So, yeah, so this routine, when routine, it's going to create two versions of it. You will have a host callable version and a device callable version. So, one point I should mention is that there will be two versions of init as well, and two versions of this, or there can be. You can do a flag to say only create device versions of these. But there will be a host version, so for init values. So if you did call init values from the host, you still have a host version to call. Routine, I'll save the details of routine for Jeff Larkin's advanced. Jeff's right here. He's got a talk later on in the GTC about advanced topics. And one is routine. Different things you can do. You can do a bind. So I could make a CUDA version of this routine, whatever it is. And you could instead, on the host, you call my version of it that's in the class. On the device, well, I'm going to call this CUDA version. You use what's called a bind attribute. You could have two different functions depending on whether it's a device or whether it's a host. So you have a way to control which one you do. In this simple case, it just creates two versions, one on the host, one on the device, and you just call the device one. But it just takes care of that busy work for you. A good question. Thank you. So one issue you're going to encounter is the data management under the hood. Now, what if you have a class which contains another class or some other dynamic? You may actually have to do a recursive copy. So think of when you have to do a copy constructor, or this is kind of like an update constructor, where you actually might have to traverse down. But it's up to you at this point in OpenACC to manage the data yourself. And this is going to get kind of hairy. Data management, unfortunately, is not well defined in OpenACC yet. But in its current state, in the OpenACC 2.0 standard, you have to actually do all the data managed yourself. So including to actually go through and traverse all your data structures, how they get copied off. I've actually done a linked list. It wasn't pretty, but I did a linked list on here where I actually traversed through all the nodes of that linked list and then copied them over individually. Performance-wise, that's not what you want to do. GPUs like long vectors, not linked lists. So that might be something you have to think about when you're designing your classes, that maybe I shouldn't use some of these structures that are like graphs because they just don't fit well into a GPU performance-wise. It's possible, but you may not get the performance that you want. Not to say you shouldn't try. Maybe in each of those nodes you've got a long vector and you want to traverse through them. That makes sense. But so here's a little bit more on routine. Routine, actually, I just showed you routine sequential. What that is creating just a device function. It has no parallelism in it. It can be called from any thread. There are higher levels. You can do a vector, worker, gang, a little bit of explanation there. Gang, kind of think of as a large group of threads. Workers is this middle level, and then a vector corresponds to a thread. If we're talking CUDA, gang corresponds to your block. Worker corresponds more to like a warp, but it can go beyond, bigger than a warp. It actually physically maps to the y dimension of your thread ID. And then vector corresponds to your x dimension. But really, it's a hierarchy. So you can have a compute region here with parallel gang calling a vector. And then what's going to happen in this vector, we're actually going to take this for loop and make it so it runs parallel across multiple threads. And then each one of those threads can call the sequential loop. So gang sequential can call worker, worker can call vector, or worker can call vector sequential, vector can only call sequential. So it's a hierarchy. But the base case that you'll most likely use is this routine sequential. So you're going to expose your own parallelism at a higher level, and then just use the routine sequential to call some function on the device. So one of the convenience things that the PGI compiler does, this is not expressed in the standard itself, is that if we see that you are calling a function from within a compute region in your class, and we have visibility to the definition of that function, we will automatically create the routine for you. So this is going to be important in things like templates that you may not have access to the code and you can't put in routine, or there are just many of them, or lambdas, something where you may not have access to the actual definition yourself. So we automatically do this for you. And I think any compiler that does implement OpenACC and C++ will have to do something similar, because there's going to be too many cases, or there's too many methods for you to have to decorate in your class all those routines. So we automatically do this for you as a convenience. So you can see some of the messages here. I should note the PGI compiler is very verbose on what it does. So there's a flag called minfo equals Excel. And that gives you compiler feedback. The compiler is telling you everything it's doing. And so in this case, it's saying, oh, I'm going to generate an implicit routine for the bracket operator. So I didn't have to actually create an operator and put a sequential on there. It's implicitly created for me. OK, so let's actually look at some examples. OK. Does this show up well there? So here's that. This is a little different from the slides, just slightly more complex, where I had this OpenACC array here. Basically what I was doing is I'm modeling this after an STL vector class, container class. So my OpenACC array is kind of a container class. In this case, it's a template, and it's being created an array of doubles. I've got here my fast push, and then I'm going to update the device, because this fast push is being done on the host, update my device with the values, then compute, update the host, print out the values that I just set there. Then I'm going to actually resize the array, or reserve more space here, and then I'm going to do it again. And I'll show you why I'm doing the resize in a second. So from OpenACC, there's not really, this looks like you would do in Fortran or C. There's not a lot of intricacies and not a lot of details, but let's go look at the header file. So in here, I've got my templated class with the different variables. Let me go down a little bit. There's the resize, the fast push, Still haven't encountered any OpenACC yet. Oh, we're down to the constructor. And so I'm going to copy in my this pointer. I actually don't copy in the data at this or anything because this is just the default constructor. But when you actually pass in a size in the constructor, create the this pointer, and then go reserve. So I have this common method called reserve where you're actually going to reserve. This is similar to what's actually in the STL vector. Here's my update classes. So I'm going to update both the size and the list of the data, depending on the type. Okay, now go down to the reserve. As I said, you have to manage the data yourself. And OpenACC doesn't, and specifically in the 2.0 standard, it kind of punts on dynamic data management. It says that's going to be something we're going to think about in the future. It's kind of a hard problem. So we have to do it ourselves. So I'm going to create this list here. So create the list. If you notice up here is the host code. You create your list, create a new one, then you take the old list and copy it over the values to resize it. That's typical. Well, I've got to mirror that over on the device. So we're going to create the list. Oh, if I need to resize it, then I need to memcopy it over. Now, in the 2.5 standard, there will be an ACC memcopy device, I believe is the syntax of there. What you see up here, the ACC memcopy is a PGI extension. You'll be able to do this in the 2.5 standard and actually in the PGI actually now. The only difference between this extension, the ACC memcopy extension, it preceded the standard version, is that we send in host pointers here. And then the standard one in the 2.5 standard, you send in device pointers. That's the only difference. But there's a way you can get down here. If you see right here, here's the 2.5 version. So you just have to explicitly grab the device pointer as opposed to the host pointer. That's the only two between the PGI extension and the 2.5. Okay, but now I've got to, on the device, copy over the data too. So you had this old list that you did a memcopy over on the device. Well, I've got to copy that data as well. That's the memcopy, device copy, or if those two aren't available, the fallback is to actually launch a kernel yourself and do the copy in a kernel. So, and then finally you delete the old list. Okay. So simple enough. Make test one. So here's all that goodness I was telling about. In the compiler, it's telling exactly what it's doing. Here's where it's doing the implicit routines. In this case, set. I didn't write a routine directive in there. It just implicitly did it. It's computed the values and then resized it and computed more. Okay. Well, let's look at a little more complex example. So here's test two. Now, what happens instead of a double, I'm actually going to create a class. So I've got this float3 class, but there's no dynamic data members in here. It's just 3 floats, so it's a float3. No big deal. I do, in this case, have to put the routine sequential if I'm going to call these routines because it's going to be in a separate class from my container class. So I won't have the visibility when I'm creating the template that these are being called. So I explicitly put them there. But now in my OpenACC array, I have my float3. And after this point, it's similar structure. Not a lot changed here. The only difference, of course, is I've got 3 values now. So pretty simple. Go through. Just go through. All I'm doing is setting the array. I know it's not that interesting of a scenario, but so let's look what I had to do to the container class. Not a lot here because it's a fixed size. So instead of a double, which just has 1, my class, my float3 class, has 3 floats in it, but it's fixed. I know the size. So really not a lot has to change in this template class, in terms of the data movement, it's still contiguous data. We can move it in one or a contiguous block. So my array or my list array didn't have to change at all. The only thing that changed, also all my data management, is the set. So here, there's an implicit routine being created. I just had to add the routine sequential in that outer loop, and now it's able to call it from the device. So it actually goes through 2 function calls. But really not a lot changed with test 2. And just to prove that it runs. OK, well, let's actually get a little bit more interesting. So now let's take that float 3, but instead of 3 floats, we're putting 3 pointers to floats. So now I actually have to put this class, the float3 array class, on the device itself. So in my constructor for this, I actually create the this pointer. And it's going to have its own allocation here. So we actually have to create the X, Y, and Z class over here on the device. So when this class is created or instantiated, we create the this pointer. We copy over each of its arrays independently. And they're attached on that array. Then we've got our set. I had to change a couple things to make these pointers. It has to have its own update device. So this class we're going to put in our container class has its own update routines. It does its own data management. Now, when we get down to the main program, that changed very little, just a little bit of structure on how that's done. OK. So let's look how our container class has to change to accommodate. So in our push, so now instead of pushing a single element onto this array, we're pushing an array, or pushing a pointer. I now, on the device, since the other class was created independent, so it has its own this pointer on the class, I've got to manually update my container class's pointer with that pointer. So how I do it is I wrote a program called setDevicePointer. I'll show you the code in a second. All it really is just you launch a kernel to set the pointer. It's not ideal, but this is how you would have to do it. And if a compiler was to do this automatically, this is what it's going to have to do. It's going to have to go in and actually manipulate your pointers so this data structure matches. So I'm creating that 3D or float3 array with its dynamic data members. It's this pointer gets created on the device, and now I have to manually attach it back to my other container class. So that's what I'm doing here. I'm actually getting the list and then elements device pointer. So this is how you get the device pointer. And then I'm going to launch a kernel under the hood and actually do the attachment myself. The size, this allows me to actually do multiple. So I could set, if I've got think of a block of memory and I want to set all the pointers across multiple, I could do that as well. In this case, it's just used to one particular pointer. So it gets a little more difficult now when we start getting into these data structures. Same thing, nothing changed with the constructor. Let's go down to reserve. Really not a lot changed because for the container class, now I've just had to, the only thing different about here is I did that manual attachment. So how it's managing its data hasn't changed at all. So the only difference now is when we get to these updates. Let me go. Is I have to, instead of, I've got to call it with a pointer. So now I'm having to understand not only is it what type is this? This is a pointer, do I have to, or is it a static class or what have you? So it gets a little more difficult. You have to actually know something about your data. And you have to do your class dependent on that data, how it is. Okay, so test 3. So once you wire it up, it's actually not too bad. I'm just printing out more numbers. Okay, now let's get really, really hairy. Okay. Now I've got this static class, float3d. It's got 1, 2, and 3-dimensional arrays. Okay. So 1, 2, 3-dimensional arrays. And I'm going to use this templated class that's an allocator. So this came out. I've got 2 of our Oak Ridge folks here that run our hackathon. So last October I did a hackathon, and Adam and I were on a team called IPIC. And one of the things out of IPIC was this array allocator. And I'm like, that's a challenge. So I decided to put it into this example. So what's happening here is this is an allocator templated class that we're going to be using to size up our 3D arrays. So now the array 1, array 2, and array 3, I'll show you the templated class here in a second, get allocated. They have their own device allocation, and we've got to now attach back to our versions of it. So we've got a PGI extension here called ACC attach. That's similar to what I did with the set device pointer routine. So it's actually going to go get that device pointer and manually attach it. Unfortunately, this operation is very expensive. We want to avoid using this if possible because we actually have to do a device synchronization right after each one of these, and that's very costly. So unfortunately, doing it this way is expensive, but it works. If you've got these really complex types of classes, now it's going to be doing its own data management. The update clause certainly can handle multidimensional arrays. I've gotten this up to, I think, 13 dimensions. But it's all handled properly. And then our host code really doesn't change much. I did a little bit of some collapse on these loops, but that's kind of irrelevant. There is no for, because, oops, I'm actually using the exact same OpenACC array class that I did for the third example. Structurally, they were fine. The only thing that changed is this other class that we're going to put into it. And then here's the allocator class. And so at the bottom level, you have the one-dimensional. Well, that's simple. We just have to create here. I did add an extra template variable, use GPU, so this can be used both for host code or with or without, so depending on how you want to use it. And then for the 2D, how it does is it calls the 1D with a 2-dimensional size and then goes through and just sets the pointer so it's pointing to the right spot in that contiguous data. Well, we have to do the same thing. We actually have to set our pointers and go through by launching a kernel to actually set all the pointers. It's the same thing you would be doing here on the host. So the same way you would set your pointers on the host, well, we've got to do the same operation over on the device and so forth, and it just recurses through. Here's a 3D array. Here's a 4D array. I think it stops there, but you could conceptually go even higher. Okay. So it's a lot of wiring that you have to do to manage these complex data structures. Okay, so let's take test 4. Okay, takes a while. There's not really any computation going on. It's just doing that set routine. But under the hood, there's a lot of extra overhead that I had to add to get these complex data structures all wired up to work properly. So hopefully, if you're going to go through if this is what your class looks like, these are what your structures are looking like, you only have to do this once, and then if you can do all your compute. So I don't want to dissuade you from doing this, but you do have to have now offset it with enough computation. So if I have that 3-dimensional array and this was millions of elements, well then, yeah, okay, I'm going to get some speed up if I run it on the device. But if these were fairly small, then the overhead you might want to do, might not want to do this. Or if you're doing a lot of data copy back and forth, you may consider a different data structure than this. I guess my point is it works, but it's not fun. It's a lot of manual operation on your part. So what are we going to do about this? And I should say that this is current state of OpenACC in the OpenACC 2.0. Let's get my slides back here. OK. So aggregate data types with dynamic data members is the proper term for this. So you have your aggregate data type, a class, a struct, whatever, any grouping, but with dynamic data members off of them. As I mentioned before, the 2.0 standard specifically actually says in one of the sections in the beginning, it says, hands off, we don't know how to do this yet. This is something we're going to look at in the future. And last November, they did come out with a technical report, 14-1, which attempts to actually solve this problem. And I think it's pretty good. It's not been implemented yet. The main concept there is a shape directive, where now you define what the shape of your data type is. So in other words, in that class, we're going to describe the data members. Because remember, these are just pointers. The compiler has no idea. They're unbounded. We don't know how big this thing is. We have no way of knowing. So there's no way we can automatically do this. We can't implicitly just copy your array over. We have no idea how big it is. Or if it's another class, that this is an array of classes, well, what's the shape of that class? We have no idea. And it could be, linked list. It could be a graph. It could be any of these data structures. The shape directive attempts to have you define, well, what is the shape? So that when we get to a copy or create on these data clauses, well, we can just follow the shape and do all this wiring that I had to do manually. It can be done automatically. It's not been ratified yet. It's expected to be a 3.0 specification feature. I think we're still thinking about it. It's a hard thing to do. It's a hard problem to manage and make sure there's synchronization between your device and your host in these complex data structures. Things like what to do about a vector. Well, a vector is taking anonymous data types. Well, as I saw, I had to build my vector class, my OpenACC array class, and I had to redesign it based on whether I was passing in a pointer or it's a fundamental type, whether it was a complex structure. I had to know something about my data. In a vector or any of the container classes, you have no concept of what the data is that's being passed to it. It has no concept of what it is. So we would really need to have that shape attribute on, or shape directive for that class you're passing in order to do anything automatically. Well, and there's another thing that it actually may become a moot point here soon. NVIDIA introduced a new feature called unified memory, a CUDA unified memory. And it's still experimental at this point, or very early. But the concept is, OK, we've got these different memories, the GPU memory and the CPU memory, that you have to manage back and forth. Well, what if that could be managed for you? So your view, you the programmer's view, is just one memory. Now, you don't have to do the attachment. You don't have to do the complex data management. You can just use a host pointer, and then when you're on the device, use the host pointer, and you have access to it. That's the concept behind it. Now, in our 15.1 compiler and our 15.3 that just came out, we have a beta package that you can download. If you go to our download pages, that's the bottom link that you apply to your Linux. It's Linux only, 64-bit only, CUDA 6.5 only. There's a lot of caveats to this. It's experimental. You should treat it as experimental. We've done, even going from 15.1 to 15.3, we made a lot of improvements to it. First thing people did when they downloaded it is they put it in a profiler, and we couldn't profile it, so we figured out what was wrong there, and now we can profile it. We also, in 15.1, it was limited to device 0 and only device 0. We've removed that restriction in 15.3, so you still can only do one device at a time, but at least with MPI, you can do multiple devices, one from each thread, and assign it, and it'll still work. Some other caveats, though, is that it's only dynamic data. Only dynamic data. So if I've got a class, a higher level class, that is statically created, I still need to manage that this pointer. Any dynamic data in that class will be managed by the unified memory manager. So if at the topmost, if I create a new class, anything with new and delete will be managed by the unified memory. Okay? Other caveats is that the memory size. First time you launch a kernel, all the managed memory goes over to the device. All of it. So therefore, you are limited to the amount of memory you have on the device. That's the amount of dynamic data that you can do. So it is a severe limitation right now. So there's no paging involved. There's no so it's the other thing is you can't do asynchronous. In order to prevent race conditions, you can't access from the host that memory from the host at the same time it's being accessed on the device. Any memory, not just what you're using. Any managed memory. So if you do that, it will crash. It's not a safe thing. Again, experimental. This is experimental. It's to get you access and make it easier for you to start moving your code over now. Future generations of NVIDIA products will have better support. NVLink, if you have access to it, will have much better support. I also should mention that your data is always late because when it gets moved is when you access it. So therefore, it's got to do a page fault and bring the data over at that point. So don't expect your speed to be optimal. But so what we're thinking now is to use data statements as kind of a prefetch mechanism. So you can still use the data movement clauses to move your data over earlier, so it'll be there so you don't have to fetch it later. But in cases where it's too complex of a data structure, you can still get it over and still utilize it. You just may have a performance cost of copying the data. So hopefully with NVLink, that will be less of a factor because it's going to be faster access between the two, but it still will be a factor. So one of the things John's mentioned is I work on SPEC, Standard Performance Evaluation Committee. We do benchmarking. One of my benchmarks that I worked on was the SPEC Excel. And this is an OpenACC benchmark, and we decided, well, let's apply unified memory to the SPEC Excel benchmark. We didn't take any of the data clauses out. We just ran it as is with the flag. And you can see it really didn't change much, but the ones that it didn't change much, it's because it was all static data. There was no dynamic data in those benchmarks, so it was irrelevant. It did slow down considerably. SP is from NAS parallel benchmarks. It does a lot of data movements and a lot of creation and deletion of data in this particular benchmark. This is the Fortran version. Interestingly enough, SWIM actually sped up. SWIM is a bandwidth test. It does a lot of data movement between the host and the device, lots of updates. And we would have thought that would slow down, but actually it sped up. But that is an artifact of pin memory. It had nothing to do with unified memory. Unified memory by default uses pin memory. We don't because of pin memory can actually slow things down if you're doing a lot of allocates anew. Pin memory speeds it up if you're doing one alloc and one dealloc and then lots of copies back and forth, which is SWIM. So this is an artifact of not unified memory, but pin memory. So, okay. So what would your class look like? Well, first, here's the flag you use for PGI. It's Tesla managed. And then you would enter your data here, exit your data. So still want that this pointer, so to make it, because this is going to be a static class itself. But you notice I didn't have to do any data management with data. I didn't have to delete it. Those update clauses are gone. I don't need those update clauses. It's no longer needed. With the 2 minutes I have left, I'm just going to go back to those examples really quick. Let's go first. So my include directory, I consolidated I didn't have to have all the different versions of my allocator class or the container class. There's just one now. If I look at that allocator class, there are no OpenACC directives in this. None. This is all dynamically. So this is back to the original version in IPIC. I really wish I had unified memory at the hackathon. That would have been very nice. Would have got over a lot of problems. In here, you can see I have a couple, depending if you're set or not, so I know a little bit, and I just have to manage that this. And notice here I do an update of the this pointer after it reallocs, because the one thing is on the device, that data pointer is the old pointer. So I need to update the host pointer on the device. I do still need to do some synchronization just a little bit within my device. So that I still had to do an update of the this. But because it's doing a shallow copy, I'm copying the host pointer over, and I can access that host pointer on the device. So you may have to do a couple little things. In a code from Sandia, I see that uses unified memory. There's a lot of these update thises in there whenever we reallocate. So let's go back to that test 4, that really hairy one. And it's actually faster. Unified memory in this case is faster. Remember, though, I have a lot of overhead here of having to do that ACC attach, doing all the wiring of all the pointers. There's a lot of overhead. I have to remove that overhead, let the underlying unified memory handle it, and therefore save myself a lot in this particular case. Now, moving forward, if you're doing a lot of copy back and forth, well, maybe doing the underlying wiring is what you want. You have that available to you. But at least your initial port, your initial experience with OpenACC and C++, you can concentrate on the compute and not the data management, given all the caveats. But OK. So I am almost out of time, so I just wanted to touch upon a couple quick things here. What we're actually working on next is function pointers and virtual functions. Those are not supported as of yet. We really need to get those wired up and working before you can have true classes and virtual functions at all. It's a big topic, a difficult problem, but we're working on it. Other things is, well, what do we do about container classes and algorithms? Are they even the correct way of doing GPU programming? Don't know yet. Might not be what you want because of some synchronizations and race conditions that could occur because you don't have control over that. What if you have 2 threads doing a resize in parallel? That's a problem. Well, what about a parallel for each? Well, is OpenACC really the way to go for a parallel for each? Maybe make it just at least interoperable with parallel for each, but the compiler can do other things under the hood for a parallel for each. Performance tuning. Once we get it all, the data management and virtual functions, now we got to concentrate. Well, the whole point of using a GPU, using NVIDIA GPUs, is because you want that speed up. You want that performance. There's no point in doing this if you're not going to get faster performance. So you may have to start thinking about your classes and how you're structuring your data, that how you've been doing it may not be amenable to the GPU. You may have to concentrate on that algorithm. And that's, I think, one of the conclusions of one of the groups at our hackathon was they need to go back and relook at their algorithms because they weren't right for a GPU. So summary, unstructured data regions or unstructured data lifetimes, the routine, this pointers. So I think I've got a few minutes left for questions.